I'm going to hand over now to Brandon, who's going to take us through stable metal isotopes in mineral exploration, gearing lab capabilities and practices to meet industry standards. So please take it away, Brandon.
All right, thank you, Helen. Is everybody all good with my screen here?
Yep, we can see you.
All right, well, yeah, so first I just wanted to say thanks to Helen and Rick for having us on here. And then also I should thank Ryan, because he covered a lot of some of the really basic stuff that I can now skip, so that's really great. So yeah, as Helen said, I just wanted to talk a bit about stable metal isotopes in ore exploration, but actually more from a pragmatic or a practical standpoint, as opposed to looking at case studies and applications and things that have been done. And I'll also talk a little bit about where we're going, hopefully, but more from a lab standpoint and less from in the field itself. And so that's why this is sort of subtitled Retooling Lab Capabilities to Meet Industry Needs. Just as an indicator, I've sort of left this little box up in the corner open. I know with the Zoom webinars and things like that, sometimes it's nice to actually have a face going on since we're not really meeting in person at the moment. So that's going to be sort of left blank throughout the presentation for anyone who wants to do that. I left Georges Agricola up there because he was the first person to really sort of articulate how a lot of ore bodies form and how they get concentrated in fluids and then deposited that way. And as such, there's sort of these secondary components, but that's just a bit of trivia for what that's worth. So summarizing in very broad strokes, some of the things that Ryan covered really well. There's some general rules in isotope ore vectoring, and some of this is empirical, so this is from what we've seen in the field, but a lot of this is actually based, as Ryan hinted at, in theoretical calculations, because ultimately isotope fractionation is really beholden to thermodynamic processes. So oxidized phases will tend to be enriched in heavy isotopes, and that's because shorter, stronger bonds will favor the heavy isotopes, basically because this decreases the overall energy of the system. Fluids and organics will tend to be enriched in heavy isotopes, say for metals, relative to their source. So again, there are caveats there, such as when you're dealing with skarns or something like that, where you have redox considerations. Downstream distillation usually will lead to isotopically heavy residues, and that's because you're releasing or getting rid of your light isotopes first. And then that follows with typical precipitation sequences, say for sphalerites in stages or something like that, or chalcopyrites, is that you will start out with lighter isotope compositions and move to heavier ones as you go to later stages. And those are just basically kinetic and energetic considerations that are at play there. So your light isotopes will tend to go through reaction pathways faster, and they will also travel faster, and so they will be the first ones to go out. And then what is left over to precipitate out later stages will be then, by mass balance, isotopically heavier. That's not really all there is to it, but that's all I'll really touch on at the moment. And then I just put a little asterisk there at the bottom. I mean, this is really just one example, but as you saw from Ryan's talk, there's really a lot of caveats in here, and things like recharge and changes in redox state, changes in your carriers. So whether you have chlorine or sulfates or something like that, that can really sort of tinker around with things. And so those are considerations that we really have to look into. So this is basically just illustrating that diagrammatically. And so we've seen a lot of this, and a lot of this work's been done with copper and zinc, and just sort of summarizing some of that work anyways. What we can see is that oftentimes as you move away from the cores or the high-grade ores, hypogene ores that is at least, you'll tend to get enriched in the heavier isotopes of something like zinc and copper. And you will tend to see enrichments in heavy isotopes of copper towards supergenes and in overlying waters. And then again, when you have redox considerations, so say you're moving from oxidized to reduced phases, you might see a dispersion or a dichotomization of, say, going from high or enriched in your heavier copper isotopes to enriched in the lighter isotopes. So that's really most of what I will say about the vectoring of this, because I really wanted to take this as an opportunity to be a bit more conversational, since there's a lot of industry folks in the audience. And so this here is just going through a tiny bit of history from the technical side of this. So multi-collector inductively coupled plasma mass spectrometers have really been around, or quote unquote widely available, since the early 90s. And there have been multiple options to choose from since at least the late 90s. And high precision metal isotope analyses, specifically that for copper and zinc and then iron, a lot of this actually stems largely from one paper during the same era, and that was in 1999. And this is based around the fact that in order to get the resolution that we need, we actually have to purify out the element whose isotopes that we're interested in, because that allows us to get much better analytical resolution than we would otherwise get. And then I'll just note too that actually in this sort of foundational paper, it was already recognized that there would probably be a lot of potential for looking at these metal isotopes in things like ore samples and in sediments, and then also medical samples, but that's a bit of an aside. But this was already there from the get-go. So that actually raises a pretty legitimate question, which why hasn't this become, over the last 20 or so years, sort of an industry standard, or at least a complementary tool that goes into the box for ore exploration? So I am definitely not an ore geologist, but I can do the best that I can to sort of slip into those shoes and try to look at this from that standpoint. So again, going with the paradigm of looking at copper and zinc isotopes per se, we've got a couple of phases that we might be interested in looking at. So I've just thrown up here chalcopyrite, sphalerite, and pyrite. So already we have sort of 3 degrees there, or 3 variables that are at play. There are, of course, a lot of different types of ore deposits. So we have these sort of archetypes, and then within those, there's actually a lot of variations on a theme. And so sort of putting that into a back of the envelope calculation, and this is of course very rough and actually quite a conservative estimate, but just assuming that all of these are independent and singular variables, and assuming that the operative order here matters, which it almost certainly does for isotope ratios, that means you've got at least 40 or more possibilities for the ultimate isotope ratio of say a given mineral in a given deposit of a very singular simple type. So now when we start thinking about things like heterogeneity, that could be micro or macroscopic. You look at recharge, changes in redox, alteration, deformation, et cetera, et cetera. And again, just taking the ones that are up here on the screen as sort of singular finite variables, that gives us a more complex environment, but still a rather conservative one. And this means that we now have 100 possible outcomes for the isotope ratio for each sample. When we start deciding that we actually need to take a more comprehensive or holistic approach to this, look at multiple elements and or isotope systems, have a large sample cohort, look across multiple similar or different deposits, that really just balloons out somewhat beyond control, at least for current capabilities. So that sort of outlines the problem, I think, from the ore exploration standpoint, is that we really need to build these really broad and dense foundations that we can build on, so we can figure out where metal isotope systems are going to be useful and where they're not, and where they're maybe a bit too complicated to be economically viable in terms of actually using them as a vectoring tool. So now I'll just switch quickly and talk about this from through the lens of the isotope geochemist. And all of what I just said really amounts to what I've labeled here the Achilles heel of conventional isotope geochemistry. So isotope geochemistry is pretty time intensive. It takes a lot of time in the lab, generally speaking anyways, using conventional methods to actually purify all of your samples, digest them, et cetera, and finally end up with your isotope ratio. So the amount of unique samples a really ambitious isotope geochemistry process or project is usually something around maybe 50 or 100, 200 if really aspirational. If we're looking at samples from drill core or drill cores, and especially if we're wanting to develop, say, a cross-sectional understanding of a deposit, that really goes up to, 1,000, 10,000 or more. And really what this is defining or underscoring is a really quite severe scalability and workflow capacity problem for the isotope geochemistry side of this. So with that, I just always like to put a brief intermission, especially when I'm sort of changing gears into these talks, because the rest of this is going to basically talk about how we can actually try to approach and overcome these issues. And not to give a spoiler, but I really think that we're right now on the cusp of actually being able to do this and making it a viable tool for vectoring. So just a bit of background here. This is a diagram just showing basically what is available to us in terms of workflow strategies that we can potentially scale up to meet the demands of industry and really take a crack at using these metal isotopes as vectoring tools. So the simplest would be this sequential extraction IEC, which is ion exchange chromatography. So again, going back to that Marischal et al. 1999 paper, basically the deal is we need to purify our elements because it gets rid of a lot of interferences, some of which we understand, some of which we don't, that basically throw the resolution of our analyses out of whack. One of the easiest way to get more bang for your buck is you have one sample solution, and from that you try to isolate out more than one element. That's basically all this is showing here. So in the example again of that 1999 paper, you can actually do this for iron, copper, and zinc from the same sample aliquot, and that's something, or variations on that theme have actually been used quite a bit to try to overcome this time and procedural bottleneck. You can also use a vacuum where you're basically just pooling everything through your ion exchange column. And quickly, since I didn't really explain what that was, more or less what we do is we digest our samples and then we put them on a resin with sort of known properties where we can stick it on there in one acid or solution that in the best case scenario is going to very, very strongly bind the element that we're interested in and let everything else flow out. And then afterwards, we will switch the pH or the molarity or the acid altogether, and then elute the element that we're interested in. And there are some variations on that theme as well, but that's the idea. So we can speed this up to a degree using a vacuum. Likewise, we can use a pump, so we can make this pressure driven. And these function more or less the same way, and there are some practical issues with these in that you tend to not get as good a separation with these techniques as you do if you go slower. But it can still be quite handy and sort of alleviate some of these strictures. The other way to do this is to automate and integrate the whole system. And so these automated systems, some of which are out there, and I'll talk about a bit later, are essentially oftentimes including both this sequential extraction and a pressure driven system, and then automating the whole process. And this can really make things a lot more streamlined and viable, both in terms of time, but also in terms of money, and time is money. So there are all of those. However, there are some other ideas that we can think of how to go about this. So something that I've spent a fair bit of time now on is trying to figure out really quick, cheap, and easy ways that we can increase our efficiency in the lab. And so that amounted to the development of really, I guess, a completely novel technique where basically we're just taking the most generic form of this, which is just your basic ion exchange chromatography in gravity. So it's just dripping. More or less, you can just chuck that into a centrifuge, do the same thing. As long as you're not going too fast, you more or less get the same separation. And then we can make our isotope analyses, usually with the multi-collector ICP-MS. And with this method, actually, you don't really lose anything. So you don't lose any analytical resolution or anything like that. You just gain heaps of time. So in this slide, I'll just show an example for zinc. So this is actually some published results where we've done this in the centrifuge. And I won't spend too much time here, but the gist is that these are elution profiles. So on the y-axis is just the total amount of whatever elements are in here. I've lumped everything that is not zinc in as the matrix, but this is sort of your major and trace elements that you want to get rid of. And then we've done that here for gravity, and then also in the spin chem or the centrifuge model. And what you can see is that more or less you don't lose anything. So as you move along the x-axis here, that's the volume of solution that we're putting through the columns to try to separate out zinc from everything else. And you can see these are more or less the same. The biggest difference is that under gravity conditions, this can take anywhere from 4 to 10 hours. And if you just do it in the centrifuge, it takes about 90 minutes. More importantly, and I guess more relevant to what we're talking about today, you can do this for copper as well. So this is unpublished work that I'm continuing here at JCU, and the idea is the same. So these are exactly the same type of elution profiles. What you can see is that this, again, goes a lot quicker. But the real novelty in doing this is that this is using a different resin than it's traditionally used. And basically what you can do, especially say if you want to look at groundwaters or something like that, you don't actually need to digest it. Most likely you can just acidify that water sample and then run it through your separation and potentially even send it straight to the mass spectrometer. And that really gets rid of a lot of time and a lot of procedural work. As I mentioned before, there are these automated platforms which really shouldn't be discounted here. So I'll spend just a moment talking about that. So these basically do all the work for you. And the really great thing about these is they have these cartridges, so the resin columns that have been really meticulously worked on by technicians to be able to separate out numerous metals in a very short period of time. And so these are multiple parallel avenues that we can take. So just making things go faster, but then also trying to automate it and tease out a lot of elements from the same sample solution. The last bit that I'll talk about here, which Ryan sort of set up for me, which is really nice of him again, is that we want to try to develop more simplified ways that we can actually determine the isotope ratios of our samples. So traditionally this is done with the multi-collector ICP-MS. Gives you really great resolution, so 0.005 to 0.01% or 0.1 per mil. You need to do your ion exchange chromatography. The gist is that this is expensive and the instruments can be quite fickle. The reason the resolution here has been so fine-tuned is because for a lot of these elements, zinc, for example, they tend to not really fractionate that much in a lot of systems, say during partial melting or something like that. So people like to squabble over differences that are more or less at the limit of our analytical resolution. However, as you've seen from Ryan's talk, where we're looking at excursions that are on the order of multiple per mil, we really don't need this level of resolution. So it's just a question of our instrument and our analytical capabilities being fit for purpose. So another option here is to actually use a quadrupole ICP-MS, which a lot of the people in the audience may be a bit more familiar with. So this basically just uses a set of column magnets to mess with the oscillation of the ion beams for anything you don't want to analyze so that you get rid of them. So this is sort of an electronic means of doing your exchange chromatography, if you want to look at it that way. And then you just look at your analyte. And you can do, more or less the periodic table in about 10 minutes using a quadrupole ICP-MS, as opposed to 7 to 10 minutes or something like that to get one isotope ratio with a multi-collector. So it's a fair bit faster. The resolution here is anywhere from, say, 5 to 10 times worse. But again, since we're looking at deviations that are also at least an order of magnitude larger, that actually just scales. So this is actually still quite viable. It turns out that this has been done already actually for zinc, which is really great. So we know that this is actually possible. It seems that you do actually still need to purify your samples, even though you have the quadrupole that is separating things out for you. But you actually don't need to do as good of a job. So say getting copper purified from a brine or seawater or anything that's got a lot of, say, chlorine and sodium and things like that in it, you basically don't have to do this over and over again ad nauseum to get a super pure solution. You just need to get enough out of there that the instrument can then take care of the rest. This is much faster, cheaper, and a heck of a lot easier to use from the technical side. So just to sort of sum all of that up, these are the tools that we have to try to make this actually work and really scale things up to be able to run, you know, not 10 or 20 or 30 samples a day, but really try to pack this out, or at least meet the capabilities of the instruments that we're using, because there's a big mismatch there right now. So looking at a complete workflow, we can look at doing microwave digestions to make that go faster. And then also we can look at these automated systems, these sort of simplified higher flow rate systems, and potentially linking this straight into an instrument and hopefully a more generic or an easier and friendlier one to get our isotope ratios where we don't actually need the analytical resolution that is generally given with the multi-collector. So I think I'm more or less right at my time limit there, or just over. So I'll actually just leave it at that. And thank everybody again for your time and attention, and open it up with questions and leave some acknowledgements there on the screen.
Fantastic. Thanks, Brandon. So we do have questions for you. It is expensive to obtain metal isotope, is more expensive to obtain metal isotope data than traditional geochemistry data. How do we breach the gap?
Yeah, well, that's the exact problem, and why I want to use try to use a quadruple ICP-MS to do isotope ratio. So most geochemical data these days comes from a quadruple ICP-MS. And at the moment, I actually don't know from an industry standpoint how much it costs to do those analyses, but I would guess anywhere between $20 and $100 a sample, depending on who you're working with. I know ACS, I think, is a big company around here. I also know that those companies don't tend to have multi-collectors on hand, so when you ask for isotope data, sometimes it can cost quite dearly. So the point is that if we can switch the instrument actually that we're doing this on, we can bring the cost down to more or less the exact same as what it would be for just your trace element geochemical analyses. And that's because all of the overhead really gets a lot cheaper if you speed up the process, because the biggest cost really is people's time more than anything else. So when you cut that down, then you can make things more affordable.
So as a follow-on question from Matt, there is another one that's popped up, but I'll just quickly ask, at JCU, where you are you able to take industry samples as a commercial service? Yeah,
so the way the AAC, so the Advanced Analytical Center here works, one, it's nice because it's actually a centralized facility, so that's pretty good. So they're actually really well equipped to take on external work, and I know they do a fair bit of that. So right now, the project that we've got going on in Mount Isa with the copper and zinc isotopes, that's actually a bit of a pilot project. One, to see what's there and what's viable in terms of using the isotopes for vectoring, but it's also a means to sort of cut our teeth on the analytical side. So right now, what I'm building up are those capabilities in the lab and testing out and building up the use of the quadruple for doing these analyses. So long story short, the answer there is yes. I'm not the person to see about booking that out, but it is certainly possible and something that we're actually trying to expand on at the moment.
Cool. I'm sure Bruce might have something to say about that in a moment as well. We have one more question. Just curious, what's the typical precision of copper and zinc isotope ratios done via quadrupole ICP-MS? Perhaps you mentioned that, but I missed it.
Yeah, so it's about an order of magnitude less precise in general than the multi-collector. So we're talking about something like 0.1 per mil, as opposed to, or sorry, 0.5 to 1 per mil. So your analytical resolution with the multi-collector on a really good day be something like 0.05 per mil to 0.1, as Ryan sort of said, and your longer term resolution's a bit worse than that usually. And with the quadrupole, it really scales to about 5 to 10 times that. The really promising thing there is that ore deposits outside of the human body and organisms, I guess, in general, ore deposits do quite a good job at fractionating metal isotopes. So if there was ever a place that we could apply techniques that don't require or that don't yield the same analytical resolution, this would be it, which is why I'm pretty excited about trying to actually bring that together.
And then Ian Wolf is asking, is qualified manpower in the lab an issue?
I think it always is. Yeah. I think isotope geochemistry, I have found anyways, seems to be, it's quite a masochistic field, or it can be at times anyway. So it can take a lot of time. That's, I guess, another facet of trying to make things go faster, because it's anyone can imagine spending 8 to 10 hours sitting in a brightly lit white lab staring at fluids drip is not most people's idea of an exciting day. So if we can make that faster or make it work for us, and at the same time as we're doing other things, I think that will alleviate that as well. But it seems like there's more, because there's more exposure, I think, to the field itself in the last maybe 5 or so years. So it seems like there's more people interested now anyway.
All right, thanks, Brandon.